Everyone to our webinar today, which forms part of the UK Freshwater Quality Research Programme. And at Leeds, we oversee this programme, and here is just a reminder of the 5 projects that form part of this. And over the earlier part of this year, we heard from each of these projects. But going forward for the remainder of the year, we're going to be hearing from other researchers and organisations that are, interested in freshwater quality, both from a research perspective and a policy perspective. So as always, you can engage with the programme. If this is your first webinar, welcome. I know many of you have been to many of them before, but there's many ways you can engage with us. There's our email address, freshwater@leeds.ac.uk. We've got a website where you can actually listen to previous webinars. They're all there on the website. And we have different social media platforms. But really it's, And as I said, we've got the next webinar is coming up next month, not so early, midday, 23rd of October, and we'll be hearing from Julia Knapp at Durham University about river quality shaped by land-river connection in a changing climate. So, as always, we reach out to everybody, and if anyone here in the audience today would like to give a webinar, please do get in contact with us. So, it's with great pleasure that I welcome Professor Richard McDowell from Lincoln University in New Zealand to give us a bit of, I suppose, a perspective in New Zealand, where he's been looking at monitoring and detecting changing water quality to, I suppose, meet policy objectives. So I think it's very pertinent to this research programme, actually, where we're, engaging with policymakers, regulators, and wanting to ensure that the research we're doing has impact. So it'd be great to hear from you, Richard, about what you're doing in New Zealand. So over to you.
Thanks very much. It's nice to be here. I'm hoping you can see everything in the right format.
It's oh yeah, that's it. It's great.
It should be coming up. It's the delay, I'm 12 hours ahead. But nevertheless, I was actually just speaking to Finn a couple of minutes ago. I couldn't honestly remember what I had promised to deliver. That may have been because I've just finished 8.5 years being Chief Scientist for Land and Water secondment, and part of that is advising both policymakers and leading other scientists to deliver good science-informed policy, especially around freshwater. So often I get hit with a question, what do we need to know? It's more pertinent now that that we've got a decent amount of science done to say, what do we need to do? Okay, so the following presentation, it's fairly hot off the press. I only gave this to the Minister just about 10 days ago. So what it'll do is go through a logic chain of what the issues are and how we solve those. So, first question that you need to ask in any sort of policy analysis is, what's the problem and what's our likelihood of fixing it? So what I've got here is a stylized diagram or map of our long and skinny country, stretching from effectively the Orphine Isles down to Morocco, if we were to transplant in the Northern Hemisphere. But it shows you a map or an estimate of the effectiveness of different measures, actions, to influence and reduce the quantity of nitrogen going into our rivers and lakes. We've also done it for phosphorus as well, and it's done relative to a current baseline with established measures that are easily done and established plus new or developing measures. The map on the right is after you take that 34 to 36%, and it shows you that around 10% of our agricultural land won't meet the limits, at least won't easily meet the limits that they set a few years ago. Of course, governments change and those limits change as well. So we've had to come up with a process which is adaptable to both the wishes of politicians and the wishes of communities. Prior to doing that, and indeed over the last 15 years, has been an emphasis on actions. And it's reached the point now where this is the last piece of legislation that has survived all government changes, and so it's still intact. And this, I guess, legislation requires every farmer in New Zealand over 20 hectares if it's a pastoral or arable use, or 5 hectares if it's horticultural, to have what they call a freshwater farm plan. I'm just going to call it a farm plan. And what that farm plan is, it maps the risk of freshwater contamination associated with your practices or your activities, the local catchment in terms of its biophysical characteristics, and the risk, i.e., what contaminants are of major concern. They are certified by regulators and audited on a 1 to 3 year cycle, depending on your performance. So we're not necessarily taking into account the targets or goals. We're just saying that they are there and we have to work towards them. But we do have to have a process whereby we are able to identify what actions are applicable to a property, to a farm, implement those in the most efficient way, and then a couple of other factors which often get left behind but are very important. And the first one is maximizing our chance of detecting change, whether that be degradation or improvement. And then finally, attributing those improvements, hopefully they're improvements, back through to the farm actions, thereby giving farmers the encouragement to do more action or maintain what they're doing. And these are all supported by a range of actors. In the farming space, you have both the farmers themselves, you have sector bodies, industry bodies, levy bodies effectively, that might support the dairy or the dry stock industries. And you have the catchment groups, where it can be communities plus farmers, and then the councils or the regulatory authorities, effectively your environment agency if you're over there. Second step, which is around selecting those farm actions, says in the legislation or in the policy that they must identify the applicability of those actions to the farm, consider their placement and timing, their co-benefits. I'll just give the example there on the right-hand side associated with reductions in nitrate leaching and greenhouse gas emissions. How long the actions are effective for, importantly, their cost effectiveness and their unintended consequences or trade-offs. For example, if you were to plant a lot of Pinus radiata in a headwater, that might be great for reducing nutrients, also very good for reducing stream flow and impairing fish survivability. When we move to planning and implementing those actions, we place a lot of emphasis on the inherent risk and also the management risk. The management risk, we will look at critical source areas, which is a concept that's got its 25th birthday at the moment this year. And that concept identifies areas of high risk that account for a small amount of a farm or a catchment area. And they normally commensurate with where you've got an area that is prone to runoff and you're putting on, for example, dirty water or dairy shed effluent, as we would say. So focusing on those areas, you might get an equivalent amount of reduction in contaminant loss, but importantly, the impact on earnings before interest and tax, or EBIT, is about 6 or 7 times less. Of course, if you're already using some of those actions, that improvement, the relative improvement, will be different. But importantly, by focusing and targeting those areas, you get better cost effectiveness. So that's written into our legislation. The other aspect about those farm plans is that they must be measurable so they can be transferred between farms, between catchments, and between regions. uh, we will say, okay, what's the risk? But it's a quantifiable risk. It's not a qualitative risk. And so although there are processes and planning systems that focus just on management, without putting them in a biophysical context, you can have the same risk associated with two different soil types, one being deep and one shallow, and hence you'll get an erroneous answer in terms of risk. So they've got to be quantifiable, not qualitative. We also make the point, at least to politicians, that farm plans, in addition to mapping those risk of losses, may not be enough to meet targets. And I go all the way back to that second slide I showed with the little red areas on the right-hand side, indicating that 10% may be too difficult to meet. So we then shift towards the detection side of this. And this is just a very simple diagram indicating what is current practice here in New Zealand, and globally this is the most common practice anyway, where you're taking monthly samples. And of course, if you happen to be taking it on a storm event, you'll get a higher concentration, for example, sediment or E. coli or phosphorus, than if you were taking it on a base flow. And hence your likelihood of detecting an accurate load over the year will be impaired by the number of samples that you take, or indeed the likelihood of detecting a concentration trend, again, has the same issue. And I'll just emphasize that, or give you an example here. We did some numbers looking at all sites in terms of rivers, groundwaters, and lakes. And these are just the data for rivers. And this is saying, okay, well, if you were to meet the policy targets, how many samples per year would you have to take over a 5-year period or over a 20-year period to meet that policy target? Remembering that we would only have 12 if it was once a month. So over 5 years, nitrate, it's not too bad. It's close to that 12 per annum, whether it's either 5 years or 20 years. E. coli, though, because it's so much more variable, we estimate you would need, on average, 4 to 6 times, depending on the site, more samples over a 5-year period and fewer over a 20-year period, because you have a total number that's greater than the 5-year period. So that has some ramifications. The third, there are 3 of them. The first one is that you have to take more samples if you want to be able to detect that change. You could change the targets, and be honest, politicians and policy folk do that, and that's fine too. Or you can take more samples in sites that are sensitive to land management actions, the old canary in the coal mine. So just to give you an example of that, this is a website, monitoringfreshwater.co.nz, which answers a lot of questions that are given to us, such as how many samples do I need to take in my catchment in order to detect change, or what's the minimum level of change that I can detect, or how much of my load is actually coming from high flows, and hence how accurate is my load. This is just one example where folk have come along and said, okay, of the manageable load, which is 0 to 100%, which is in the middle here, they've selected nitrate and nitrogen for a catchment. Indeed, this is where I live, near Christchurch in the South Island. And they said, over a 5-year period with monthly sampling, what's my statistical power? Remembering that anything over 80% is what we want to achieve. And if we were just doing that, 5 years of monthly sampling with a 30% reduction, which is a common policy target, it's very unlikely over the majority of the catchment that you would achieve that. There's one stream down in the south where you would do that, but elsewhere not. Increasing that to weekly over a 20-year period, you get an ability to detect that level of change over that period. Of course, if you had a greater change that you wanted to detect, you would have a higher likelihood of doing that as well. So that's detecting change. The final thing that we go through is attributing those changes back through to actions. And of course, it's not just actions, but there's also climate and lag times that have an effect. All these three things need to be taken into account before attribution can be robustly determined. Climate is quite a significant player or influence of water quality trends here in New Zealand. We're an oceanic bunch of islands in the middle of the Pacific, 3 hours flight from the nearest landmass, Australia. So we're at the whims of climatic cycles as they are influencing our local seas and oceans. The Southern Oscillation Index is one such example. And you can see here the change in water quality trends at two sites where it's very in sync and somewhat out of sync. And so we know and have looked at this oscillation and can therefore remove climate from the influence of water quality trends, both in surface and in groundwater. Lag times is another issue. And here's a very simple representation. What we have is data at a macro level at around 5 kilometre square grids of nitrogen and phosphorus and other contaminant losses across the country since 1990. And so we've been able to track land use change and track likely losses. What you have here is dairy losses of nitrogen, the load of those, relative to other land uses, which didn't change. And you've got an increase in those, the upside down triangles, well before the load in the river, in the outlet of the river, in the Waimakariri River, is happening, roughly around 5.5 years later. That's the simplest explanation of what a lag time is between changes on land and when you're detecting it at the outlet of this catchment. On average, our catchments have a lag time, surface water lag time, of just under 5 years. Many smaller ones, it's within a year. Larger ones, it can be 10, 12, 14 years, but on average, just less than 5 years. So we have data here for 5 catchments, dairy dominated, high signal to noise ratio in that respect. There's a lot of dairy goes on in these catchments. We have been looking over a 20-year period at their water quality and then also looking at practice change through regular surveys, agricultural surveys we call them, every 3 to 4 years. There's also farmer engagement and knowledge exchange over a period. And we decided to give that knowledge and farmer engagement in a defined period and then let them go to it. And so we said, okay, we've identified what the main problem is here and provided advice around what you could do. So here's an example of one of those catchments. You'll note these contaminants are on a log scale, and so that slope is actually quite abrupt. The upwards arrows are when there were shifts in dairy shed effluent infrastructure. So a group of farmers did one change, another change, another change, another group. That's what those up arrows are. When we stopped giving and monitoring when those changes were occurring, the water quality plateaued. And so this is evidence that the advice is seeping through, pun intended, to actions, and then those actions are having an effect on water quality in those rivers. There are other practices associated with grazing cows on grass or on crops in winter. That's what we call wintering. And then also irrigation efficiency. By that, it's water irrigation efficiency. So when the advice was stopped, water quality improvements stopped. So this is, I guess, our first concrete evidence is despite all the noise and the signals, different signals coming in, that when the advice stopped, water quality improvements stopped. Just on the bottom left-hand side, that's just an indication of how much it cost us to deliver that advice. So I'm going to give you, just to finish off, an example with groundwater. Again, this is where I live. In fact, my house is just on the right-hand side of this picture on the bottom left. And this is an irrigated area. It's about 150,000 hectares. It is 95% dairy. And that's because the current profitability for dairy farms here is about £500 a cow per annum. So there's a lot of money to be made. In fact, I think this year it's 27 billion. But here's what happens. This is for a bore. And what you have on the left-hand side is a typical regional authority approach. A local authority has looked at these data and they've just simply plotted a trend line through it and said, oh, well, everything's fine and dandy. And then an NGO comes along and says, okay, well, we'll cherry pick the first 5 years and we'll say there's a big problem here, isn't there? And then the irrigation scheme, which run a collective consent, have cherry picked the last 5 years and said, oh, there's got to be an improvement here. The problem is that climate was changing during this time as well. And in fact, recharge was only 20% of normal. That means that there was an awful lot of storage happening in the soil and it wasn't pulsing through. So the irrigation company, which holds a collective consent for people to discharge nitrogen, the way that they act upon that is that they have farm plans. Okay, so they've gone through a similar sort of process that will be done nationally, but they sort of pioneered this. And these are the results. Now, for a farmer to get an A grade, they're doing everything right whenever someone turns up. They get a B grade, there's one thing that someone's found is, well, you could probably do an improvement. C or D, oh, mate, you've got an awful lot of work to do. We might turn your water off. It also means that if you were to have a C or D, you get visited far more frequently than if you are doing an A. Collectively, across the scheme, all these plans add up to a 30% reduction in nitrate nitrogen. And that's what they are complied with. Now, for just one of those sites, on the left-hand side, on the top left-hand side, you have a breakdown of where those farm plans have done load reductions, okay? So that's why you've got different colours. These represent different blocks and different farms. The wedge of cheese relates to the capture zone associated with that well, that red dot. In that well, you have the nitrate nitrogen concentrations in that plot. Okay, so these are sampled over a period of time. You also have, through that farm plan, estimates of how much nitrate was being leaked from their operation. So that's the blue line, blue dashed line. They have a peak in their losses before the groundwater peak. Now, much like there was a surface water lag time, groundwater lag time, this is a fairly shallow bore. In fact, it's about 10 meters deep, so it's likely to have a short lag time. And indeed, this indicates that because they were starting to do remedial actions in around 2018, 2017, 2018, the peak was before you saw the peak in groundwater. That's another expression of lag time. We confirm that by taking tritium data. And indeed, the tritium data was telling us that the age of the water was around 2.5 years old in this well. Recharge, of course, alters what the concentrations would be. And so if it recharges and pulses that stored nitrate through, you'll get an increase in the concentration. So you can adjust the concentration accordingly. That's what that red dashed line is. You then, because you know the lag time confirmed by both practice and groundwater sampling and also the tritium data, and you know what the climate was doing, you can adjust the well data to the right and in magnitude according to those effects. So you've removed the effect of climate and you've controlled for lag time in that effect. What you end up with, therefore, is a decrease in concentrations that are real. So in that example right at the start, when someone was saying, oh, it's increasing and decreasing, well, actually, they were both right. But it is now decreasing because there are actions taken in that wedge of cheese contributing to this groundwater well. So this is just some of the data in some of the groundwater wells and when they are likely to change. And so after you've taken climate and lag times out of the picture, you're only left with actions. And we are likely to see change in these locations. There are many more, but they range from we're seeing them now to we are unlikely to see them in many people's lifetimes. And now that could be for a couple of reasons. The primary one is that they're being influenced by the nearby river. Another one is that they're normally pretty low concentrations anyway, and they don't vary. So there's not likely to be a good chance of detecting change anyway. So those are a couple of examples and indeed an outline of the process as we've done it thus far. Just to conclude, I mean, farm plans, as we've been using them and indeed how we are going to use them are an excellent way of linking farm actions through to water quality improvements. They do that when you do it in that process by providing information about where and when improvements can be done and setting people's expectations or clarifying people's expectations that it's not going to happen next year, but it will happen eventually. By doing that, it enables you to put emphasis on implementation to make sure that we have the best chance of achieving those improvements. And of course, we recognise that additional actions or remedial actions may occur over time. We haven't got a monopoly on knowledge, and there will be always new actions arise. But the effect of these can be included within this process. So that's what I've got. That normally takes me about half an hour because that's the attention span of most of the politicians I deal with. Hopefully, it's good for you guys, and I'm perfectly happy to answer any questions as well.